Time's up. It seems that we're not following that clock over there, but some GPS locked clock on somebody's wrist, not mine. Anyhow, we will have a nice presentation of a generic gigahertz transverter / controller, and we'll also have a demonstration which is missing one test signal, they say. So the demonstration is working, there's just nothing to demonstrate it on. So here comes the signal generator. It's off, but it will be on soon. Presenter will be Hamish Kellock, OH2GAQ. So off you go.
Sorry to do this to you and stay a bit late, but it's more interesting to have a demo if there's some signal there, usually. That one. And about -60 dBm. And 144.8. Okay, so this organised talk the plain one. Okay, first I should introduce myself a little bit. My name's Hamish Kellock. I used to be VK3ZMV back in the 1960s, so that explains the white hair. And I've been living in Finland for about 33 years, minus a few years living overseas, working overseas. And I've been a very inactive radio amateur for, let's say, for 20 years. And then the last 10 years, occasionally I've started to do something again. And one of the things that I've been interested in is how to get a box or something that can be used with microwave transverters to provide all the features that you probably normally end up having, you know, one of these and one of those and another one of these and something else in order to get the transverter to work. The sort of things that you need. I think this is a bit busy slide. Anyway, whatever it is, it should be able to receive and transmit SSB, CW, maybe FM. Maybe that's enough, but other things may be useful. You want to know the frequency that your transverter is working on, what your transmit frequency is, what your receive frequency is. It might be nice if it actually told you that frequency in real numbers. You know, you don't have to add something to some number to come up with the right answer. It should be accurate, and especially for some of the sort of computer-enhanced modes, you want to be able to be sure that the frequency is within so many hertz, maybe 10 hertz, maybe less, of the frequency that you want to be transmitting at or receiving at. It wants to be able to provide the sort of push-to-talk or Vox or computer-controlled transmit-receive functionality. And I think that because some of the higher power microwave devices tend to be very expensive and rather sensitive to antennas falling off them or feed bits of coax burning up, you can protect them in the first case by having some isolators and stuff there, but it might be a nice idea that if something goes wrong with the system and the VSWR goes up, that everything's turned off pretty quickly to protect that expensive device. And in my case, I said, okay, let's limit it that it can control at any one time 4 different microwave transverters. Maybe you'll have a lot more than that, but 4 is a good number. And it should be battery powered, if possible, because you may want to use it up in a mountaintop or hilltop, I guess, in Finland. Not so many mountains. And I sort of alluded that it should be controlled by an external computer, and you should be able to change how it works, either by changing hardware or maybe changing a program in the thing. And this is a block diagram of the first version of this device that I came up with, which was in about 4 or 5 years ago. And it was physically quite large. It used a separate receiver, but it basically met most of the requirements, except that it basically only generated SSB, maybe CW, but it basically only generated SSB. It was not convenient to generate other modes in this hardware implementation. And it had the rubidium standard there. And it had a 2 metre to 28 megahertz transverter. It had the SSB generator, amp and filter, DDS for controlling the frequency. It was all locked to a rubidium reference oscillator. And it had an output to a conventional 28 megahertz receiver, which could have whatever mode in it. And power supply stuff. And then I thought, well, you know, technology's changing. And it's about time to start using some of the newer technology in this thing and possibly try and squeeze the whole thing smaller and put a lot more modes into it. So you can see that this has more or less the same functionality as the previous diagram. However, there's no external receiver. It supports several modes. It supports SSB, FM, CW, and whatever other modes are programmed there. And it's based on using a SDR type implementation for the receiver and transmitter. And then it's got a number of devices that are connected into a USB hub, which is inside the box here, and it has one USB cable coming out that you can connect to your computer or whatever other control device you're going to use. And this shows a picture of what's inside this box. Anybody got a laser pointer? Sorry. Pointer? No. Okay. That's my mistake. Ah. Yeah. That's just like that. No. Anyway, if you look down at the, looking at the screen, I'm sorry to turn my back on you here, At the lower left corner, there's a rubidium standard. Above it, in the background, there is the control board, which is microprocessor based, which handles all the sort of sequencing and switching and stuff like that. Above it, there is a USB hub. You can see 3 USB cable connectors stuck into the hub. And then if we move over to the right, at the top right corner, there's a 2 metre to 28 megahertz transverter, which also can be switched so that you just bypass the 28 megs straight through it. Okay, thanks. Up here, this is miscellaneous power supplies. They take 12 volts and give out various regulated voltages for other purposes. And this is an audio, a cheap USB audio interface card. It's used for the microphone input and for the loudspeaker output. And then this is the modified P-Berry SDR. It's single, this particular one is set up for single band, 28 megahertz, receive transmit. So the actual transmit receive part of this thing is quite small and takes a very small part of the total of the unit. However, it needs one thing to make it work. This box doesn't do anything without a PC or other computing device. So this is where we try some demo. We've already had a couple of demo effects, so let's see. Okay, where's Michael? Somewhere. Anyway, we now seem to have a signal there, which we didn't have before because we couldn't get anything from the beacon here. This is coming from a signal generator. I just have to turn on another bit of software. This can all be done in one batch, but here I wanted to do it separately. So this is the system operating, and one of the features that I wanted is that all of this control stuff that you have to use mice and keyboards for to operate, I wanted to be able to use it from the front panel of this. So this is the tuning. I can swap the mode, LSB, AM, FM, etc. I can go to TX and I can allow it to be remote controlled, and I can change the band that I'm using here. So if I go away from, that was on 5.76 gigahertz, but I cheated because the 144 meg IF is plugged straight in the signal generator. So you can select which transverter you're using just by pressing a button. So for many things you can operate this without having the PC there. So we were talking about what's in the hardware before, and this is what the software architecture is like in this device when it's running on a PC. So here we have our SDR, we have our USB 2 type connection, and then we have the HD SDR software. Who's familiar with that stuff? One? It's free software, but it's not open source. So, in fact, it's very closed source, actually, but it's free. And it's quite good. But if you want something done to it, to change it, it's not so easy. You can discuss with the author, maybe, and get something done. But it's quite good software as it was, and that's what you saw on the screen before. And then we want to control the HDSR software, and we want to control the front panel of this device. And there's some more free software. Again, it's not open source, but it's free. It's called OmniRig, and it can be very easily interfaced to a lot of different types of radio amateur and maybe some professional products. And the interfacing is done in a very clever way because you basically have to write a text file that defines certain functions or how these functions are operated in the particular rig that you're talking to. So you can make your own rig definitions and then just use it. And the interface between HDSDR and OmniRig is built into the HDSDR software. So this gives you a fairly good way of interfacing that. And then you normally want to pipe the audio output and maybe the audio input to HDSDR to various places. I mean, at present we listen to it on a loudspeaker, but that's only one use because you may want to pipe it to some other software. For example, the Ham Radio Deluxe DM780 module, which is their multi-mode receive transmit module, where you can use all sorts of protocols, PSK31, various multi-tone, etc. Signalling systems. I think there's about maybe 20 or 30 different protocols supported in HD, in the DM780. Or you might want to use WSJT, or you name it. PC audio is a bit of a, I'd say it's a mess. Maybe there are others who don't think it's a mess, but I think it is a little bit of a mess, because one of the things it does is that it converts the format of your audio, maybe without you knowing, into something, and then maybe it converts it back. So it may do a couple of samplings and resamplings. But if you use something like this VUSHF, which is not free software, there is a demo version free, but you can't use the demo version in any real thing. Then basically you can specify the input bit rate, the output bit rate, and what goes in and what comes out is what you more or less expect to come in and out. And it's very easy to connect multiple clients to VUSHF, so that if you take the VUSHF output, it can actually be connected to multiple processing clients at the end of it. Okay, and then at the end, you probably want to output some audio also to a loudspeaker so you can hear it. And this is a screen from HDSDR, which you saw before. This was taken from my QTH in Espoo, and this is the 10 gigahertz Helsinki OH2GAQ, I think it is, beacon, shown here, and then in a bit more detail over here. And then this is the Morse code being decoded by the multi-PSK software suite, which is another one of these high-level software suites. I won't go through these notes, there's just a lot of text there, but it's maybe interesting at some time. But as I said, this box doesn't do anything without something of about this size attached to it, running Microsoft software, or there can be some Linux software that you can run in that. So, how to get rid of the PC? So of course there is one thing, is why do you want to do it like this? And I suppose my answer is that I want to do it like this because I want to do it like this, and this is an honest answer. I prefer to do it like this, using the SDR rather than to use a couple of external boxes which may or may not have SDRs in them. One thing is that the cost of SDRs, like this kit that I used here, this P-Berry, it's around the €120 mark. It's not exactly super expensive. What is a Raspberry Pi? Is it a PC? If it consumes, let's say, 5 volts, somewhere 1 to 2 amps, it costs €60. Maybe if you buy a display panel to go with it, it costs, total is €100, maybe. Is it a PC or not? Well, one of the things is it's not awfully big. This PC board on the back of this is a Raspberry Pi version 3 computer. The rest of it is the display. And this is a touchscreen 7-inch display. So if you use something like this, you don't, in principle, need mice or keyboards or anything in the field. You can just run it all on something like this. And again, it's $100 or €100, something like that for the whole thing. So is it a PC or not? You can certainly put it in a box and make it look like not a PC. And then the question is, does it have enough processor capacity or I/O capacity to run an SDR type application? We all know that there are plenty of dedicated SDR back-end processors using various digital signal processors and other single chip processors. But this one is particularly attractive to me and maybe to other people because it's cheap. It's got 4 USB interfaces in it. If you want to put it on a big screen, it's got an HDMI interface. If you want to use it with a small screen, you just plug this ribbon cable in the side, and it takes 5 volts at a couple of amps maximum. So it's actually quite portable. So if you look at the software for Linux Raspbian variant, there's several things available, and some of them are also available in the PC world as well as in the Linux world. How many of you know Jim Ahlstrom, who's produced some software called, or you don't know him, but you might know Quisk? No, nobody has heard of Quisk. So Quisk is a free SDR software which is truly open source. So all the source code for Quisk is available. You can download it from SourceForge. You can modify it, break it, make it better, do whatever you like. And particularly if you want to interface it to some sort of strange box like this, it seemed to me a good place to start because you can certainly, it already has some primitives there for interfacing it to external hardware. And you can certainly add more software for interfacing it to the external hardware. There's Linrad from Leif in Sweden. It also runs on Linux and Windows. And there are various upper-level Linux programs, for example, FLDigi, and there's also WSJT software which runs also in Linux. So there's plenty of upper-level software around that you can put on top of the basic SDR software. And this is, it's interesting because it's available both in Windows and in Linux environment. So this is Quisk running in a Windows PC, what's called the small screen mode. The mode changes the number of buttons and things on the bottom of it. And the small screen mode minimises the number of buttons so that if you have a screen like this, touch screen like that, it's usable for people with old big fingers and things like that. And in this case, it's looking at the Inkoo 2-metre beacon. So now let's have a look at the same PC with the same interface on it, and we'll get rid of HDSDR. Then we run Quisk. And you can see that I haven't compensated the other side of the quadrature balance at this near this frequency. Actually, I compensated it down at 144.2, and so you can see that there's a big secondary. Big secondary signal here. Quisk has several different displays. It has a waterfall display, the same as other one does. You can see there was something jump frequency there. So here's a waterfall display, etc. And you can select the bandwidth, 2000 Hertz. I don't know if you can, I think you can see that there's a sort of a slightly darker part of the screen up here, and that shows the bandwidth that you've selected at this moment. It's got a lot of controls in it, and as I said, it's free and it's open source, so you can do what you like with it. And there's a lot of pre-built modules from other people apart from the author of the software for interfacing to various rigs if you want to interface it to some particular rig.